Okay, good morning everybody. Today we continue the electric fields. Last time we have seen that if there is a point charge, plus or minus, electric fields are automatically created. And the size doesn't matter. If it is spherical in shape, the surface includes the charges and the electric fields fill all the space. And similarly, when we have a flat surface, the electric fields also are produced, not only on one side, but on the other side. So we can also put these charges on a wire and electric fields are again automatically created. If the charges are positive, the electric field lines are away from the charge, but if it is negative, then towards the charge. Suppose this is minus Q, then the electric field lines will be towards it. Now, what happens is that these kind of charge distributions modify the space. So this is the space. Here, although this charge is so far away from this point, it creates some kind of effect. So the electric field at this point is to the left, okay? Now, if you put a neutral particle here, remember that in PHYS101 we dealt with the particles like M with a mass, but no charge. Nothing happens because this electric field only affects the charges. But once you put the charge on this, okay, plus or minus, okay, then this electric field will exert a force on this charge. And this force will be given by QE. As you see, this force not only depends on the direction of the electric field, but also the sign of the small charge, test charge, let's say, Q, okay? So if Q is positive, then F equals QE, so that F will be parallel to the electric field. So the force will be in the same direction as the electric field. Since electric field is to the left, the force in this case will be also to the left. So the force vector will be also to the left for positive charges. So for Q positive. But when the charge is negative, then the force will be equal to minus QE, okay? So Q being the magnitude, okay? In this case, F will be opposite. It will be parallel to E, but in opposite direction. So the angle between the force and electric field vector will be 0 degrees here, but here theta will be 180 degrees. So for negative charges, suppose this Q is negative, then the force is this way, opposite to the electric field, okay? So it doesn't matter how the electric field is created. So these electric fields are not going to be necessarily straight. So if there is an electric field, then you can really find out what the force on the charge. So we place the charge, usually we use test charges. And by using the electric field, you can calculate the force. And if you know the force, you can get the acceleration. If you know the acceleration, you can get the velocity. If you know the velocity, you can get the displacement as a function of time. As you see, you know everything about the particle. So starting from, suppose that there is an electric field somewhere and the particle starts its motion at this point, it will move in the direction of the electric field. Maybe the electric field is not straight, but rotating. So it's possible. In this case, the particle or the charge will move along this path, following electric field lines. If, of course, the charge is positive, okay? If the charges are negative, it moves in opposite direction. But once the charge starts moving, you know exactly what the acceleration is, velocity and displacement, so that in space, suppose it's two-dimensional, not necessarily, it can be also a three-dimensional case. So the charge can move in this three-dimensional space, and then you know exactly where it will be located. This is very important. Okay, this is very important, because if you know where the particle or the charge is at t equals 0, then you can really follow the path of the particle, and you know exactly at what time, at what space the charge will be. Okay, so that's why this is a very strong method of electric field is known. So this is a really fundamental equation. The force is equal to Q times E. Once the force is known, you know everything about the charge. Okay, so let's now continue with some examples. Remember that we solved some examples before. Because the electric the effects. Suppose that we have plus charge here and then minus charge there. Okay, so let's look at the electric field at this point. In order to find the electric field at this point, we have to draw a straight line. Okay, first of all, let's write the magnitude of the electric field is K Q divided by R squared. Okay, so if this is plus, the electric field will be in this direction. Okay, for this one, let's say this is charge 1, Q1 and Q2. Okay, so electric field is away from this charge. But for this one, okay, the electric field is towards it, so that this will be E2 due to this charge, which is negative. This is E1. Now, what happens is that because there are two electric field lines at this point, then the resulting is the summation of these two vectors, okay, which is this one. So this is E total. So if you place a charge here, it will not move in this direction, it will not move in this direction, but it will move exactly to the right, because the total electric field is to the right. So if there are more than one electric fields, you have to get the total electric field in order to get the total force, okay? And if you know the total force, you can get the acceleration, velocity, and the displacement. Good. So now let's have a problem, okay? Let's have a problem in which there are two charges like that, and let's give a numerical examples, okay? Now, one is minus 50 microcoulomb, and another charge, which is Q2, plus 50 microcoulomb. This is Q1. So this is negative charge, this is positive charge, okay? And let's also put this, since this is two-dimensional, we put this axis, okay, y-axis, and we would like to find 30 centimeters above this charge, what the electric field is at 30 centimeters away from this charge, straightly above, okay? And also, this, let's say this is point A, okay? And this is right in between the two charges, okay? The distances are the same. Suppose that this is 26 centimeters and this is also 26 centimeters, okay? The charges are in the same, okay? Have the same distance to the origin. So 26 centimeters and 26 centimeters. And we would like to also find what the electric field at point B, okay? So electric field, what is EA? Okay, and what is EB? Finding the electric field, okay, here at point B is easier. It's the case like that, okay? Because this is positive, so let's connect these two charges to this point. As you see here, because this charge is positive, it creates an electric field this way, and because this is negative, it creates an electric field that way. And not only the electric field intensity will be the same for these two cases, because the charges are exactly the same, and the distances will be the same because this is an equilateral triangle. Okay, so the length of these vectors will also be the same. Okay, everything is symmetric. So now it means that if you just combine these two vectors, the resulting vector, electric field vector, will be exactly like the case on the left, will be to the right. Okay, so this is EB. The electric field will be totally to the right. But we have to be able to find this electric field by using one of them. Okay, and we know the distances. So this distance from one side is given as 40 centimeters. Okay, so the distance from point B to this second charge, or point B to the first charge, second and first, will be exactly the same because this is an equilateral triangle. So now this is the electric field. What about this case? If you look at this case, again for point A, the electric field is to the, okay, in the positive y direction because this is plus, okay, and then because this is minus, we have to now connect this point A to this charge, which is Q1. But because this is negative, then the electric field will be towards it. I don't know what the lengths will be, okay? But because now this is longer than that one, this electric field should be greater than this one. So we have to draw this as a smaller vector because the charges are the same. Because the electric field is affected not only by the distance, but also the charges. Since charges are the same, the smaller distance creates a greater electric field. So that when we combine these two, we see that the electric field at this point A, okay, will be this way. So this will be EA. So this is how you can get vectorally the electric field, okay, electric field. Now we have to find exactly how they are given in space. So EB, for instance, will be something like this as a vector. Since it is totally in x direction, some kind of value times I, okay, because it's in positive direction. But EA has this resulting vector, this, okay, this vector. So if I move this around, put here, okay, it will have two components, EA x and EA y. So this x and y components. In order to find x and y components, we have to know these angles. What is this angle? Okay, we can do that. Okay, but before that, let's find this EB because it's very simple. This electric field due to this Q2 or Q1 will be equal to, okay, will be equal to K times 50 microcoulomb, 50 times 10 to the minus 6, okay, divided by the distance, 40 centimeters, but 40 means 0.4 meters, and the square of it. Now K is 9 times 10 to the 9, okay? So let's also put the value of K here, 9 times 10 to the 9, okay? So the value of K is given here. So if you just look at here, this expression gives you, okay, this expression gives you just 2.8 times 10 to the 6 newtons per coulomb, okay? So the electric field for this one will be this much. But this is not the electric field. This is the electric field shown this way or that way, okay? So this is the magnitude of these electric fields, but it's not the actual electric field in x direction. To find that, we have to know the angle. Let's say that this angle is alpha, and we know that the y components will cancel each other, okay? So these two vectors have y components which cancel each other, but the x components will just add, so that this E times cosine alpha will be twice as much stronger, coming from the upper electric field and lower electric. magnitude, the resulting magnitude of EB will be equal to 2 times E times cosine alpha. Okay? Remember that this X component is E times cosine alpha. There is one from the bottom and there is one from the top. If you just add them up, it's twice as much. So we have to be able to find this. Okay? But this alpha, since we can use cosine, okay? So cosine alpha from here, cosine alpha will be equal to, okay, 26 centimeters divided by 40, 26 divided by 40, which is equal to just 0.65. So it's just, okay, cosine alpha is 0.65. So it's equal to 2 times 2.8 times 10 to the 6 times 0.65. And it gives you the value of 3.6 times 10 to the 6 Newton per Coulomb. So we know, okay, so the electric field magnitude for point B is given by this number. Ten to the 6 Newtons, but okay, before the unit you have to write this I vector. So this is without the unit. If you write this at a vector form, you don't need to write the units. So this will be the result for EB. For EA, it's a little bit longer, okay? So we have to remove this part and try to get it. Okay. So, first of all, we have to understand that this case is two-dimensional case. Okay. So we now have this vector here, and we have another vector down below, and this will be the resulting vector. Okay, this is EA. So this is E2, this is E1. Okay, we have to find the X and Y component of. First of all, E2, what is E2? E2 is the electric field due to this charge. So it's K times 50 microcoulomb divided by the distance, but the distance is 0.3 square. Okay, so E2 is given by this. What about E1? This E1. E1 is given by, okay, the magnitude of E1 is given by, see, I'm not putting any vector sign. It means that it's just magnitude. So we have to find this E1. This E1 is just exactly the same, K times 50 microcoulomb, because the charges are the same, divided by the distance square. But the distance from this point A to this charge, okay, is given by 60 centimeters. Okay, so it's given 60. So it's 0.6 square. But this is not the electric field. This is not the electric field vector. It's just the magnitude of the electric field vector. Okay, so if you write E2 as a vector, E2 will be equal to, okay, E2, whatever the value is, times I, J, because it's in totally Y direction, no X component, but E1 will have two components, okay? One this and the other that. So this is E1X, E1Y. So this E1 vector is not only in X or Y direction, but it has positive X component and negative Y component. So please, okay. So E1X will be given as E1 times cosine 30 degrees. Since E1 is known from this value, whatever it is, And I will just give you the result. It's 1.1 times 10 to the 6 Newton per Coulomb. So we found the x component of this E1, which is created by this negative charge. Now, what about the y component? E1y. E1y is equal to, okay, E1y is equal to just E1 times sine 30 degrees. In other words, the half of this, because sine 30 is 1/2. So you can get just whatever the value it is, you can get the half of this, okay? 2.2 times 10 to the 6 Newton per Coulomb. Good. Now, we know all these numbers, and let's also calculate this E2. E2 is given as, okay, E2 is given as, since it's only in y direction, okay, it's 4.5 times, okay, wait a minute. Okay, so E2 is just 9 times 10 to the 9 times 50 times 10 to the 6 divided by 0.3 squared. Okay, so now what happens is that this is what you get, 2.2, but the result is just 2.2, 6.6 times 10 to the 6 Newton per Coulomb. So this is the result. So E2 vector is written like that. So let's write all these vectors individually. E2 vector is given as 6.6 times 10 to the 6 J, okay, because it's in positive y direction. E1 vector is given by the x component first, 1.1 times 10 to the 6 I, because this is the x component. Now the y component is in minus y direction, as you see, it's downward, minus the y component, 2.2 times 10 to the 6 Newton per Coulomb. Is this the result? No, because the result is just the sum of these two vectors. So EA, this resulting vector, is just the sum of these two vectors, E1 plus E2. As you see, I forgot to put J there because it's negative y direction, don't forget. Only J components will be added because this is the only x component we have. So the result will be 1.1 times 10 to the 6 I, okay? And if you subtract 2.2 from 6.6, you get 4.4, okay? Minus, with a minus sign, 4.4 times 10 to the 6 J. Okay, so the electric field at point A will be given by this vector. Now, what about the magnitude of this? How can I find EA? How long it is, right? So how long it is found by this square root, okay, 1.1 squared plus 4.4 squared. Of course, you get this result times 10 to the 6. You should never forget this 10 to the 6. I didn't put 10 to the 6 inside the square root because after squaring and then taking the square root, it will give you 10 to the 6 anyways. So the result is just 4.5 times 10 to the 6 Newton per Coulomb. Okay, so as a vector, so if you so this is the magnitude of the vector, or just EA. So okay, if you do not put any vector sign above a vector, or just put